Okay, so the first announcement is that we will tentatively schedule our midterm in week 6 instead of the original planned week 4 because we had a holiday on Monday and also we're doing this remote teaching. So I'll see what the university decides to do after week 4. And also I hope that by then we can cover more materials, then the midterm can serve as a better basis for the final exam. Okay, so to continue with our lecture, so we're
I have a
actually
question about that. If we're not back in person by week 6, then will the midterm still be week 6 or will it be back week 5?
No, I think we'll do week 6 anyway.
Okay.
Yeah. So and so if we're still remote, then the midterm will be remote. So this is just to continue with our last lecture. I said we are a little behind our schedule because this time I spent more time to catch up with some background, right? So because I noticed that different 100A or different 170A, the math, or 170E, they may cover different things. So that's why we need to make people on the same page before we proceed. So to continue with our lecture, last time, and just to quickly recap, we talk about the continuity theorem, which is the foundation of what we will talk about today, the central limit theorem. The continuity theorem just connects the convergence of the MGF with the convergence of the CDF. Okay, so if you can show convergence of MGF, you can show convergence of CDF. And the convergence of CDF is what we define formally as the convergence in distribution. That means if you can say the CDF of this random variable sequence, x1, x2, and so on, converge to the CDF of a random variable x, then we can say this random variable sequence is convergent to that random variable x. So that's what we want to show. And last time we used this result to show this, the Poisson distribution will converge to a normal distribution as the Poisson lambda converges to infinity. And during the office hour, I received a question about why we want to define this lambda sequence, lambda 1, lambda 2, lambda m. So we actually don't have to. Actually, in your homework, you have done this problem, right? And also in the discussion section last time, we talked about this. So the reason why we introduced the sequence is to be aligned with this theorem. In the theorem, we have a random variable sequence. So therefore, we also want to introduce a random variable sequence as x1, x2, and so on. And so therefore, we want to have each xi follows Poisson with its parameter lambda I, and let this lambda sequence converges to infinity. So it's just a way to use this continuity theorem. And last time we stopped here. Okay, we're saying that because we want to show this random variable sequence as n goes to infinity will converge in distribution to a normal distribution. And by convergence, we know the mean and the variance will still be this Poisson mean and Poisson variance, which are both lambda n. And this lambda n is going to infinity, right? Then it's very hard to say what happens for the normal distribution with mean and variance converging to infinity. To avoid that issue, we standardize this random variable sequence by subtracting the mean and dividing the standard deviation, which is the square root of the variance. Then we want to show if the standardized sequence Zn is convergent in distribution to standard normal distribution, because for each Zn, we now have its mean as 0, variance as 1. Okay, so to go from here, we just need to derive the MGF of Zn and show if this MGF is convergent to the MGF of standard normal for any t. So t is the argument of the MGF, and it takes real values. That's the whole idea. And then last time we stopped here, we said, oh, the MGF of Zn, by applying what we said about the property of the MGF, which means that if you know the MGF of Xn, you can directly write the MGF of Zn, right, by that transformation. So with that, then we can write the MGF of Zn in terms of MGF of Xn, and we get here. So then what's left is to show this function is convergent to this function. And to show that, we just need to show the exponent without the exponential basis. The exponent will converge to this exponent. And that's what we left here. Okay. And last time I gave the hint saying that to show the convergence, on the left-hand side, you have an exponential function. On the right-hand side of t, in terms of t, on the right-hand side, you have a polynomial function of t, a square. So therefore, you want to remove this exponential function by replacing it with a polynomial function. And how we can do that is to use the Taylor expansion. So this result is exactly from Taylor expansion. And I try to say that we don't need to memorize those. If you do, that's good, right? Because you can do this quickly. But if you don't, then you can always derive it based on the Taylor expansion. And this is how it works. We are expanding this exponential x function around x equals 0. Okay, when x equals 0, this is the Taylor expansion. And then we get here. Okay, so do we have questions about this so far? No. Okay, great. So yeah, that's the purpose of having camera on. If you have your camera on, I can see your reaction. So if you have a question, then you can say immediately. Okay, so let's continue. Following this, since we did this in the discussion section, I will be quick. Just give me 1 second. Okay, so since we did this in the discussion section, what's left here is for the left-hand side, let me use that Taylor expansion for exponential function, okay? So we know this is equal to 1 plus the exponent square over 2, right? So we'll do that. So this first term stays, and the second term, I would just write it as 1 plus 1 over root lambda nt plus 1/2 times 1 over root lambda nt squared, and so on. Okay, that's for the Taylor expansion minus 1. Okay, now you see I get rid of the exponential term. I'm left with a polynomial. So if you already understand this, but this is like a recap. All right, then I will have some cancellation. First, this 1 and this minus 1 will cancel each other. And then I will multiply this lambda n into the term. Okay, so this will become negative root lambda m plus root lambda nt. Okay, plus, and you see here, after I open the square, it will become 1 over lambda n times t squared. So that lambda n in the denominator will be canceled with this one. So I'll get 1 over 2t squared. Okay, maybe I need to go to one more term and see what that would be. Okay, so I'll just add the term here, the third term. And that one would be 1 over 3. For the Taylor expansion of exponential function, 1 over root lambda nt cubic. I will have that. So therefore, with this cancellation, I will have 1 over 3, and I will have 1 over root n staying in the denominator, t cubed. Okay, and so on. So then you can see that for the other terms, they will all involve this root lambda n in the denominator. So therefore, I will introduce a notation for convenience, and that's used a lot in mathematical statistics. I will write it as small o 1 over root lambda m. So what does the small o mean? Okay, I have questions in the chat box. Would it be 1 over 3 factorial? Let me see. You're talking about the Taylor expansion of that, right? Yeah, that's right. You're right. Okay, thanks for pointing that out. So for this, then but the constants can be ignored here. We're just saying that when we write this, what it means is that this term goes down to 0 faster than 1 over root lambda n. So to introduce this notation, I'll just do this quickly. So basically, we can say that if I wrote term A is small o of term B, okay, then what this means is that, or maybe I say AN, two sequences, is a small o of BN. Then what this means is that if I take the ratio of AN over BN, and I let the limit as n goes to infinity, then this limit is 0. That's what it means. So AN goes down to 0 faster than BN does. So therefore, you can see that I can always write 1 over n squared as small o of 1 over n, right? Because this one goes to 0 faster. And also, I can write 1 over n squared plus 1 over n cubed is small o 1 over n, and so on. So we can put all the small terms, which goes down to 0 faster than this term does, into the small o, just as a way to simplify the expression. Okay, do we have question for this? It's just a notation. All right, so if not, then what we can do next is to let this lambda n go to infinity. Okay, but before doing that, we have another cancellation out here. These two terms now get canceled. So when I let lambda n goes to infinity, as in my condition, you can see that this whole term will converge to 1 over 2t squared. This doesn't involve lambda n, so it stays. Plus, now I let the lambda m goes to infinity. And inside that, I have 1 over 3 factorial, 1 over root lambda n t cubed, plus the small o 1 over root lambda n. So then you can see, because this root lambda n is in a denominator, this term will go to 0. And since this term is smaller than this term, when it goes to 0 faster than this term, so this one will also go to 0. So that's why this limit is 0. So that's why I'm having 1 over 2 times t squared, which is exactly what I need to prove as the limit. So in other words, I should. Is the question or not? Okay.
Sorry.
No problem. So in other words, we showed the convergence of the exponent of this m, z, and t to the exponent of this standard normal, right? To the exponent of the mg of standard normal. So what I'm saying is that we have shown that this log transformed mzn at any t, right? I'm taking the exponent, so it's equivalent to taking the log, converges to log mzt, right? And this z is the standard normal random variable. And therefore, as n goes to infinity, so this is equivalent of saying that without a log, I have the moment generating function of Zn converging pointwise for every t to the MGF of Z. Okay. Then finally, by the continuity theorem, we have what? Zn, okay, converges in distribution to this z. Okay, Zn converges. I'm going to introduce this notation, which you will see in more advanced classes. This means convergence in distribution to z, and z follows standard normal. So in other words, without using the mathematical notation, this says that standardized Poisson lambda random variable, a standardized Poisson lambda random variable converges in distribution to standard normal random variable, right? To standard normal as lambda goes to infinity. This is the statement we try to prove. Okay, so that concludes this part. And also I want to say that I realized not everyone in this class have written a formal proof before. Again, this is due to people's different training and background before this class. But I'm trying to say that what we are doing here is a proof, okay? So we're trying to prove a statement, and also some of our homework questions are also about writing proofs. So I would say we do not really enforce a very rigorous standard about what a rigorous proof should look like here, but I try to say that try your best to write down the steps in your logic, right? How do you go from one step to the next step and reach the conclusion? So if that's something you haven't done before, I think this class can be a first attempt and try to write down details. I think that will be my best suggestion, right? Try to write down every logic and try not to leap over gaps. All right, any questions about this? This is more like a recap of the homework and also what we did in the discussion. All right, then let's move on to our first topic, important topic today, central limit theorem. I think many of you must have heard of this from introductory statistics courses before, because this is like the most important concept or result as the foundation of statistics, but it's from probability. So let's first give you the probability statement, and then we'll talk about the statistics relevance. So here we have a sequence of IID random variables. Again, what is IID? Everybody should think about this. Identically or independent and identically distributed. So one I for independence, one I for identically distributed. Okay, random variables. Okay, with mean, because they're IID, they have the same mean and same variance. And we assume the variance is not infinity, finite. Okay, and MGF, we just give it a same MGF called MX, okay, MXT. And this argument can be T, that's what we use, but I leave it as open because it's just a symbol. Defined in a neighborhood of 0. So this 0 means that the argument must be defined in the neighborhood of 0. So this is what we need as a technical condition for the MGF to work for us. And all the previous discussion, we're assuming the MGF is defined in the neighborhood of 0. That's what we said in the first lecture. Okay. Okay, now we look at two important notations. This is something we will use consistently throughout this class. The sum of this NIID, we define this as Sn. Okay, so I assume everybody is familiar with this big sigma notation for sum, but if you're not familiar with it, I'll just say it equals to, for I goes from 1 to n, you take the sum, okay? So it's x1 plus 2xn. It's a short notation for writing this, and we will use this throughout this class. That's the sum. Okay. And also, we will define the average. Xn bar, we will use this also throughout this class. It's defined as Sn divided by n. So the average, so it's basically the average of all the xi's. Okay, this is the average. And the central limit theorem tells us this, a very interesting result. So if we consider the CDF of Sn and this Xn bar, what we can do is that we first standardize each. Okay, so standardize Sn. You will see what it looks like. So we will do Sn subtracting the mean of Sn. Okay, I'll just write it here. Divided by the square root of the variance of Sn. Okay, this is what we mean by standardization. But since we know the definition of Sn as the sum of x1 to xn, so I can write it here. Its expectation can be shown as the sum of expectations, sum of the mean of x1 to sum of expectation of x1 to sum to expectation of xn. These are all mu's, so it's actually n times mu because they're the same. And for the variance of Sn, okay, I will use the fact that they are IID, so they are independent. Therefore, none of them have any covariance. All the covariances are 0. So therefore, the variance of the sum in this independent case becomes the sum of their variances, which are all sigma squared. So this is equal to n sigma squared. And I received a question about under what case we can assume the variance of the sum is equal to the sum of the variance. And the answer is that when the variables in the sum are independent. So therefore, the covariances are 0. That's the special case. Okay, so that's what we have. And then finally, let's go to this Xn bar. Because we have this 1 over n multiplied to Sn. For the expectation, the multiplier applies to this, right? So then it's 1 over n times this n times mu. We get mu. And for the variance, okay, this constant will be squared, right? So this is equal to 1 over n squared times the variance of Sn. When the constant gets out of variance, it must be squared. So therefore, this is sigma squared over n. Okay, so I want to make some discussion about this result, which is very important. So which means that here you have n IIDs, and when you take the average of them, the average still has the same mean as each individual variable has. But the variance of the average is actually the original variance divided by n, which means that as your n goes large, the variance of the average becomes small, right? And you can see as n goes to infinity, this variance is going down to 0. So this is a very important result, and its relevance in statistics is that if we consider we have n observations, that means we're doing a measurement of some quantity of our interest for n times. And these n measurements are conducted independently, right? Using the same instrument, that means we can assume they follow the same random distribution, which is the distribution of the measurement error. All right, so in this case, it means that if we have those n measurements and we take the average as our final result from this instrument, then this average is becoming stable and more stable as n goes to infinity. And this stability means what? means that if I perform the experiment n times, and then you come and perform the experiment n times, so I can have my average, you can have your average. Let's compare our two averages. The numbers could be different. But if we both increase our n to infinity, then our two averages will become equal. So that's the intuition behind this whole idea. What does this xn bar variance mean? It means that if we repeat the experiment for many times, and each time I have n measurements, okay? So each experiment will give me one average, and we compare the averages across experiments done by different people, then will this average become more stable if we increase the number of measurements by each person? Is there different meaning? No. The bracket and the parentheses were used exchangeably. It's just different textbook or people have different habits. Yeah. Okay, but related to that, I want to emphasize the notation again. When we talk about expectation variance, what's inside the random variable must be capitalized. I want to emphasize that a lot because I saw in a lot of questions people sent, they still use lowercase in the expectation. If that's the case, then when it's simple, then people know what you mean. But when it's complicated, it could confuse people, right? So for example, if I have this, let me just grab another piece of paper. If I write this, okay. So what this means is that I'm taking expectation, but I'm treating y being equal to lowercase y as the conditional. So in this case, I'm just treating y as the small y as the constant. Okay, then the only random variable I care here is the capital X. So in this case, because it's a constant, I can move it out. So it becomes y times the expectation of big X given y equals small y. Okay, so in this case, you need to be very clear what is treated as the random, capitalized, and what you treat it as a fixed, and that's lowercase. Okay, so this is something I want to emphasize about notation, but the bracket and parentheses doesn't matter that much. Okay, so coming back here, these two results are very important. So this is what we have for standardization. Now I put in the values, so it becomes Sm minus mu divided by, you see, put this into the square root. I have root m sigma. This is the standardization of Sn, the sum. Now I will do the standardization of the average. And let's see what we get. So this is xm bar minus expectation of xm bar over square root of the variance of xm bar. Okay. And then let's put in the values again. So this is xm bar minus mu, okay, the square root of this. So that will be sigma divided by root n. Okay, now my question for you is, are these two things equal to each other? It's an algebra question. Actually, I will use the definition of this xm bar to relate to the two terms. Okay, so how about I write it this? It's basically Sn divided by m. That's the definition of xm bar minus mu. Okay, so what I can do is that I multiply m to the numerator and denominator. If I do that, I do the multiplication both, then the numerator becomes Sn minus mu. Okay, and the denominator, if I multiply by n, that can cancel this root n in the denominator and leaving a root n here. Okay, so then you can see they are the same. So what I'm trying to say here is that if you standardize the sum, or if you standardize the average, you get the same thing. Okay, so these are equal. And then what the central limit theorem, coming back to this, what the statement is, the CLT statement, it says these two things which are equal. Okay, I'm right here. Okay. These two things, if I let n goes to infinity, let n go to infinity, both will converge in distribution to standard normal. That's the important statement. Okay. And that's the thing we will use a lot in practice. So what it says is that no matter what the distribution of your random variable sequence is, as long as you have variance as finite, then you can show that the average will follow distribution more and more like the uniform distribution. The symbol above the arrow is the D, is what I said here. I first introduced here in today's class. I said that means convergence in distribution. And convergence in distribution is defined as the convergence of the CDF. That means the CDF function of Zn is convergent to the CDF of Z. Okay, so that's what we are saying. And last time, it's basically this. This is the definition of convergence in distribution. Okay, and there is a technicality I specified last time. It's about the convergence at every x for which this limiting CDF is continuous at. And last time I explained what we mean by a CDF is continuous at, right? If you recall. So yeah, so I would say in our previous lecture notes, I tried to avoid using this notation arrow D because in this class, we didn't formally introduce what is convergence in distribution, because there are other modes of convergence. If you take a more advanced probability class, you will see that. But here, I just want to say that it means that the distribution intuitively, it means that the distribution of this term becomes more and more like the distribution of standard normal as n goes to infinity. And at the end of today's class, I'm going to show you some R examples so you can see this visually, what it means that this distribution is more and more like. Okay. Okay, so that's the central limit theorem statement. And again, the relevance to statistics is that you can consider this is a sample of n observations you obtain, and you calculate the sum or the average of your sample. So that's a number, right? This is a number, this is a number. But what we're interested in is that what if I collected more samples by doing this whole procedure repeatedly? So that will give me another number of the average whenever I repeat. So these numbers will give me a distribution of this ratio. And what I wonder is that what this distribution of this ratio is. And this theorem tells you, no matter how your original distribution is like, it could be exponential distribution, it could be Poisson distribution. As long as the distribution satisfies the variance is finite, then the average after standardization will have a distribution more and more like standard normal distribution as the sample size n goes to infinity. Okay, so what I want to emphasize is that if you have only one sample, that's what we call the realization. If you only have one number for each xi, then you will only have a number here. So with one number, you cannot talk about distribution. So the whole idea of distribution is our imagination when we do statistics. That means we see beyond our data. We imagine potential data that were collected under the same process from the same distribution. Then our observed number is just one of those numbers. But we are interested in the collective behavior, all the potential data, how they look like. Does that make sense? I think that's the most difficult part for thinking about statistics. Honestly, you have to see beyond your numbers. So that's why we need this mathematical statistics as a tool to really do the imagination. Otherwise, if we only see numbers, what we're doing is just operation. Okay, and that's what everybody can do using a calculator. We can calculate the mean, we can calculate the standard deviation of the numbers, but these numbers is just what we see. And we are interested in knowing what we don't see by imagining there are potential samples. So for example, making it more concrete, I have my n numbers, but I'm interested in what happens in this whole class. Okay, so that means if we have 50 students, we will have 50 averages. Each of us will have one average, and we're interested in how those 50 averages collectively look like. And that's the distribution we're talking about. Okay, so hopefully this will make more sense after I show you the R code later. So this is the central limit theorem result. And some of you ask, why do we need to study the MGF, right? That's a mathematical tool. And here you will see it's used again. We will use the MGF as a tool for proving the central limit theorem. I believe that even if you learned this from an introductory class, you have not proved it before. So that's why we're going to do it here, to show that, yeah, this really we can do it, right? This is a very classical result, but with the MGF as such a useful tool, we can prove it in this undergraduate class. Okay, so what I'm going to do is that I'm going to start with the MGF of this ratio, okay? And again, show that this MGF is convergent to the MGF of standard normal. So I'm going to write a proof here. So first, we give this ratio a notation. We call it Zn, so that can make things simpler for us. Okay, and since we are going to derive its MGF, here the random variable is Sn, so we will rely on the MGF of Sn. And MGF of Sn, we know it's the sum of IIDs, and we have seen that result before. So we can relate the MGF of Sn to the MGF of each xi, and which we have is mx. So therefore, what I'm going to do is that I first write down this as a transformation, which is minus root m times mu divided by sigma. Okay, I'm getting this term out, which is not, it's a addition to some term about Sn, and plus 1 over root n sigma times Sn. Okay, the reason I write it as A plus B times Sn so that I can apply that transformation. Okay, so therefore with this, I can have the MGF of Zn at t is equal to, by that property of MGF, is equal to exponential to the negative root n times mu over sigma t times t times the MGF of Sn at 1 over root n times over root n sigma times t, right? I'm just applying that result. And what I need furthermore is based on the independence assumption, I can write as MSNT because, I'll write here, because, you know, this MSNT is known to be the product of the MGF of xi's, right? And they are all equal to the mx. So therefore, this is equal to mx at t to the power n. I'm going to use that. Because of that, then this can be further written as exponential, the first term, I just copy it, times mx at this 1 over root n sigma t to the power n. That's it. Okay, and then that's the thing we have. And our goal is to show that this mznt as n goes to infinity, I put this, as n goes to infinity, will converge to the MGF of standard normal, which is we know is exponential 1/2 t squared. That's what we want to show. So now you see that we have this exponential function here on the left-hand side, exponential function here on the right-hand side. So to show this, it's sufficient to show that if we take the log, so we can remove the exponential function, the technique we used once. Log mznt would converge as n goes to infinity to the log of the right-hand side, which is 1/2 t squared. Okay, that's what we want to show. And then you see, taking the log, another good thing is that we can get rid of this power. It can come down. Okay, so what is the log on the left-hand side? If we do it, we can see that it's actually negative root n times mu over sigma t plus n times log, okay, log of mxm at 1 over root n sigma t. And what can we do? So you see, we are basically here, and our goal is to show by some steps whether this will finally converge to 1 over 2t squared as n goes to infinity. So what happens as n goes to infinity is that this root n will go to infinity. That's what we know. But we have this mxm, which is a form, right? We know this is an MGF, but we don't know what's exact form. The reason is that I'm saying those x, oh, sorry, I shouldn't put in. This n should be gone. mx, sorry. Yeah, so this mx can be any MGF as long as this MGF is defined in the neighborhood of 0. Okay, so that's the power of central limit theorem. We are not limiting to a specific form of the distribution of those IIDs. So mx can be any MGF. And then how do we open this log, right? That's something we need to consider. And furthermore, mx, how do we get rid of it? So these are two questions we want to answer. And also a condition we haven't used yet in the proof is that those IIDs have mean mu and variance sigma squared. All right, so for those, we also need to use that connection to this MGF. So first of all, let's try to remember, how do we connect the MGF to the moments in our first lecture? And you also tried that in your homework too. And the answer is Taylor expansion, right? Once we do Taylor expansion on the MGF, we can connect the MGF to the moments. So let's worry about this term first. Okay, so let's say recall that Taylor expansion would give us mx at this quantity. I will just write t over root n sigma. We expand it as 0. Okay, plus by Taylor extension, I would have t over root n sigma. It should be this argument minus 0, but since it's 0, I just ignore the minus 0 times the mx prime first derivative as 0. And second order, that would be 1 over 2. It actually be 2 factorial t over root n sigma squared times the second derivative of the function as 0. All right. And then one more thing, I'll just go to one more term, 3 factorial third derivative as 0, and so on. Right? So this is the Taylor expansion we are familiar with. And by the definition of the MGF function, if you recall, then the MGF function evaluating at 0 is always 1. Why is that? The reason is that if you see this, the definition, right? We did in the first lecture. When t is equal to 0, the exponential function becomes 1. So that's why mx at 0 is always 1. This is a fact. Okay, and we will put the fact here. So this is 1. And for this one, we know this is the definition, or this is equal to the moment of x, first moment of x. So therefore, I put it as t, right? The first moment of x is given in our condition, which is mu. I put it here. Okay, and second order, this one. Okay, this I know is the second moment. Okay, this is what we know. And also what we know is also that the second moment is equal to the first moment square plus the variance, which is means mu square plus sigma square. We also know that. So therefore, this term can be written as, okay, I'll go to the next line. I will not disrupt this line. Okay, and furthermore, for the third term, I would just keep it as 1/3 factorial. Okay, for this one, it's actually, I'll put here. Okay, and so on. This is what I have for this. So basically, you can see that I would have this thing by Taylor expansion, okay, as this. So what's next is that based on this log function, I will also try to remove the log. The reason is because, you know, for the limit here, I'm going to show the whole thing convergent to 1/2 t squared. And the problem is that on the right-hand side, the limit, the 1/2 t squared doesn't involve any log. But on the left-hand side, I have the log. So I need to remove the log. And another thing to think about how to remove the log and make it polynomial, Taylor expansion. So we'll use Taylor expansion again on the log function. So basically, we use Taylor expansion first to remove what we don't know about the MGF, the MX, this specific form, and we make it into what we know as the mu, right? And also sigma squared, those will come out. And also, we will remove the log function by use Taylor expansion, so it becomes polynomial. So then you can see how important, what important role Taylor expansion plays in this mathematical statistic, right? Because whenever, so the key idea is that whenever we want to get a polynomial from an arbitrary function, we use Taylor expansion. Okay, so next thing is that for this log function, now I put it here, okay? So this log function of mx, this thing, because of the above line, now becomes log 1 plus t, okay? And 1/2, now I change to a factorial to 2. T over root n sigma squared. And now for the second moment, I will put it as mu squared plus sigma squared. Okay. And now for the third term, I will keep it okay. Now, how do I remove the log? To remove the log, what I will use is this. Taylor expansion for this 1 plus x. Okay, so if I expand it at x equals 0, this is the function I do expansion. So then it's basically log 1 plus 0, right? Expanded x equals 0 plus x times the derivative d dx log 1 plus x. I take the derivative at x equals 0. I'm using this notation because here I want to say specifically I'm taking the derivative against x. And I would do the second term, 1 over 2 factorial x squared. Now it's second derivative, d squared dx squared log 1 plus x, evaluating the second derivative at x equals 0, and so on. Okay, and now you can see what the simplification would be. Log 1 is 0, and this is x, times the derivative, it should be 1 plus x over 1 plus x. That's the derivative, right? And I evaluate that at x equals 0. It's basically this. I evaluate this derivative at x equals 0, and I know this is equal to 1. Okay, and for the second term, see, 1 over 2 x squared stays. What's the second derivative of this function? So I'm going to take the derivative against this, of this against x again. So it's actually negative 1 over 1 plus x squared, evaluating this as x equals 0. Okay, and so on. So these are all calculus basics, and we're using them, right? We're not trying to teach how to derive them, but I will leave this as something you want to maybe try to review if that's something you haven't used for a while. So therefore, for this second derivative, when it's equal to 0, it's basically negative 1. So therefore, this Taylor expansion will give me x minus 1/2 x squared, and so on. Okay, so a lot of people, when they do the approximation, they stay at the first order. So that's why you will see a lot of people use the fact that when x is small, okay, when x is positive and small, a lot of people do this approximation a lot. So try to approximate log 1 plus x by x. Going back to log 1 plus x, why did we decide to do Taylor expansion on it? The reason is that we want to show this whole thing converges to 1/2 t squared. And 1/2 t squared doesn't involve log terms. It's just a polynomial. So that's why for the left-hand side, we want to remove log and just keep polynomial. That's the reason. So why? The reason is because we are having this term is log 1 plus something, right? So we want to remove it. So therefore, we want to just leave it with a polynomial. And this is a known fact. I'm just trying to derive why we have this known fact by not assuming everybody knows it. So that's why this is like a basic derivation of this fact. But if you know it, you can use it directly. Does that make sense? Okay. Okay, so with this, now let's coming back to here. Okay, coming back to here. So this one, okay, but be assured that this proof about the central limit theorem is probably the most complicated one we'll do in this class. Okay, so that's why it's kind of lengthy, but you should feel very proud of yourself that you can prove this classical result as an undergraduate student, right? Thinking about this way, then you will feel like, wow, I'm so amazing. So coming back to here, then using this result, just try to consider this whole term after this one as the x. Okay, consider this whole term in the box as the x here. So therefore, this can be, use the Taylor expansion as itself. Okay, so I will just write it down. Okay, maybe I'll just write it down as the box. Okay, plus minus, my bad, minus 1/2 box square. Okay, and so on. So let's first understand this at this high level. Then let's put in what's in the box. So the box, the first term is t over this times mu. Okay, and plus 1/2. Now I'm going to open the square. It's n sigma square in the denominator, t square in the numerator, times mu square plus sigma square. Okay, and for the third term, think about it. If you open the cubic, then it will be root n cubic, right? So in the denominator, you will have n times root n, which goes down to 0 faster than 1/n. So for the third term, I'm just going to put it as small o, 1/n, without worrying about specific form, because it goes down to 0 faster than n, 1/n. Does that make sense to everybody? So I want to make sure people are staying here. So for this term, once I open the cube in the denominator, I will have root n times n, right? I have 3 copies of root n. Then it's root n times n, which goes down to 0 faster than just having n in the denominator. So essentially what I'm saying is that this thing is small o 1/n. That's exactly what it means. Okay, so this is what I simplify from the box. And then second term, minus 1/2. Inside the box, I'm going to take the square of each term. And here, the key is that I only keep the terms that are in the order of 1/n. For all the terms that are small o 1/n, I don't write them out. How do we know that goes faster? And why is 1/n? So let me answer those 2 questions one by one. So first, the question is you're asking why this holds. The reason is that if you divide by the definition, right? So if you divide, if you do the division here, this ratio of this over this, then what you will get here is 1 over root n, right? And the limit of this is equal to 0. That's why. That's the definition of small o. Okay, coming back to...
Then how about 1/n?
1/n goes down to 0. What's the question? We're saying the
my
small...
My question is, you say that like for third term, 1/n cube is, you say the mentioning like it goes faster. So I don't know the meaning of the meaning of the faster.
The faster is what I said in the previous page. Let me go down to here. Can somebody help me find it? Let me see where it is. Sorry, so can somebody remember? Sorry, okay, I'll just write it again. So remember I said, okay, maybe I'll get a different piece of paper, not to confuse ourselves. Remember I wrote this, right? I said the definition of an is small o bn is defined as the limit that an over bn as n goes to infinity is 0. That's the definition of going down to 0 faster. So this means an goes down to 0 faster than bn does. Did you get this part? Okay, now the AN is this left-hand side, BN is 1 over N.
Oh, okay. I'll figure out. And then what is the O? Is it not 0, right? What is the
Small o, small
Yeah.
o. So that's why I feel like we have a lot of back and forth in the class. So that's why I hope that whenever I say something, people pay attention. If you don't understand it right away, just ask the question right there. So that can be that, and so that we can stay on the same page, right? And if you think I go too fast, you can let me know.
Yeah,
So
I'm
small,
trying to focusing on this class, and then all the things is quite new for me. So even though I don't understand right away, but it takes some time to understand what meaning
yeah,
of this. Yeah, you know.
exactly. So I feel like this is something probably everybody should give a feedback to previous classes. That's what I guess, because what I'm teaching here is actually based on a standardized curriculum we coordinated. So the prerequisites are supposed to provide a foundation for this class. If not, then I think there must be some issues with the curriculum, especially the previous classes. So that's why I think that's something we need to receive the feedback from you guys and see what we can do better for this whole curriculum, the major. Yeah, because this is not the first class of the major,
Yeah. So
And also,
yeah.
and also I want to emphasize how important math is. Yeah, so that's the problem. If you take the 100A poker one, okay, I will leave this to you as an option, right? Because I don't want to force everybody to take this class right now or not. It's your decision. But I'm just saying that the poker one doesn't offer enough foundation for this one. I can say that for sure. You will need to know the continuous random variable. If you don't know it, so that's why I put that Harvard class as the, at the link in the CCLE. And that's for everybody's benefit. And you need to know the background. But if you're not ready to, okay, so the questions you're raising in the chat box is out of my control. So that's why I couldn't say much. I cannot say much about it. But that's something you could give the department as a feedback. That's my suggestion. And I will try my best to help everybody stay on the same page, but I will not try to force everybody. So that's the thing. I'll give you options, but I will not make the decision for you guys. But still, I want to say, especially for those of you who consider going to graduate school with a major in statistics, this class is a must. Okay, but you don't have to take it right now if you think you're not ready. And also the videos will be online anytime. So hopefully I will make the learning not so much painful for people. But the math is just, math, right? It's a math stats class, so we cannot get rid of math. But let's put it this way. This proof is the most difficult one in this whole class. So that's why if you feel it's very challenging at this time, try to rewatch the video and maybe you'll feel it better. Okay, so then if you find that any time you're confused, just raise your hand and I'll be happy to answer your question. And also back to the Vincent's question, let me go back to the chat. How do we go from -1/2 factorial to 1/2 factorial? Okay. So you are talking about which part? So this is the -1/2 factorial from the log, right? But this 1/2 is from the box, it's from here. So that's why they are not the same thing. So what I'm saying here is that, okay, I'll make it clearer. This is the box. We're just talking the box here. And now I'm going to talk about the box square. So that's the -1/2.
Thank you. Got it.
Okay, yeah. And there's another question from Le Han. I think this expansion of the, okay, I see. Thanks for, she's replying to Vincent's question. All right, so watching the Harvard lecture. Okay, so that lecture I'm saying it's to help you. It's not definitely, it's not a it's not really my demand, but I just hope everybody can learn this one better. So that's why the background will be essential. So speaking of teaching this class, right? In the previous year, I even encountered students who didn't know what is an exponential function. So in that case, I would strongly suggest that making up the background is necessary. Otherwise, we will use exponential function, log function all the time, right? How can we deal with this? So thank you. Yeah. Thank you, everybody. So let's try to make this learning effective. And also, please know that we will not try to discourage people or intimidate people. That's not the whole purpose. But we try to make sure that this material makes sense and you think it's reasonable and valuable to learn those things. Okay, coming back to the box square. Now let's do it. So think about these three terms. Now we're going to square them. And what I want everybody to focus on is whether each term goes down to 0 faster than 1 over n. Okay, so if this n has a power greater than 1 in the denominator, then it will go down to 0 faster than 1 over n. We pay attention to that. It's necessary that we simplify the term so the term doesn't become too long. So now in the square, okay, in the square, we would have this term being squared. That will give me t squared over n sigma squared mu. Okay, and I will also have the second term squared. You see, when I square it, it becomes n squared. So it's going down to 0 faster than 1 over n. When I square the third term, of course, it will go down to 0 faster than 1 over n. So therefore, the square of this term and square of this term can all be put into that small 1 over n. Now, the cross terms, 2 times this, that will still be, 1 over root n times 1 over n. That will go down to 0 faster than 1 over n. Also, this one crossed with this, still going down to faster than 1 over n. So it's the cross of this and this. So therefore, except the square of the first term, that's the order, on the order of 1 over n. All the remaining terms will be small o 1 over n. They all go down faster to 0 than 1 over n. Does that make sense? Yeah. Okay. And for the cube term, right, the box cubic, which is going to be in the tail expansion as the ... these will also be, I can tell you, small o 1 over n. So this is something, if you go to the graduate school and you learn what we call the asymptotic statistics, and I covered the class for twice. In the course number, we call the 203. It's called large sample theory, which is also called asymptotic statistics. They are all dealing with this n goes to infinity case. So therefore, we think about the order instead of the actual constant. And do we square the mean? Yep, nice catch. We need to do that. Yeah, so this mu should be squared. All right, so now I'm going to simplify everything. To do the simplification, I will group the terms that has 1 over root n and group the terms that has 1 over m and the terms that's small o 1 over n. Okay, so therefore you see, I would have t over root n sigma mu. For the term with 1 over n, it's this term and this term. So I will have plus 1 over 2 t squared and sigma squared, mu squared plus sigma squared, minus 1 over 2 t squared and sigma squared mu squared. Okay, these things are the only 2 terms involving 1 over n. And finally, we have small o 1 over n. Okay. And now for these 2 terms, we can have some cancellation. So you see this mu square and this mu square, they can be canceled, right? This is algebra. So I'm left with 1 over 2 t squared and sigma squared, sigma squared. Okay, that's it. And small o 1 over n squared, 1 over n, sorry, I left it here. And now you have see I have this and this, these two things canceled. Wow, so you see, we simplify this term, this complicated term, to the so much simpler term, right? That's the magic of Taylor expansion. You can simplify a nonlinear function to a polynomial. Then finally, coming back to this is what we want to prove. Could you please repeat the name of the theorem, central limit theorem? Is that what you mean? We are proving the central limit.
No, I mean, you said the theorem that we learned in the graduate.
No, it's not a theorem. We say the asymptotic statistics or large sample theory. That's
okay.
what it's not a theorem. It's just a topic.
Okay, sorry about that.
Yeah, no, it's okay. Yeah, it's good to ask. That means a lot of cases, I mean, this is a core of classical statistics, right? So what we do is that we care about, we are interested in what the statistic will behave like if we have the sample size goes to infinity. That's the ideal case. That's when we have unlimited resources, we can collect the data unlimitedly, and then how would the statistic behave? That's the ideal scenario of our study. So later, when you see we talk about the doing hypothesis testing, then we will use the asymptotic distribution of statistic as a way to calculate p-value, etc. So actually, to put it here, we can actually say the standard normal is the asymptotic distribution of this ratio. So it's another way of saying this ratio is convergent in distribution to standard normal. Okay. Okay, so coming back to what we want to prove here, you see, so this log of the NGF of Zn, the ratio, okay, plus n times the log nx at this. Okay, that's what we have, right? Did the squared become 0? The mean squared becomes 0. What do you mean? What do you mean by mean squared becomes 0? Mean squared minus variance squared? No, we didn't. So it's actually about this part, right? So I'm just saying we're combining those two terms, and you can see that this mu square and the mu square here will be canceled. So that's why we're left with just sigma square. Okay, so coming back to here, then this term, we will just replace it by what we have here. Okay, so you have and n. Don't forget, this are n here, and what we have here is the log. Okay. Right, that's what we have. And then we have another cancellation. So you see, if I open it up, I would have root n times t over sigma mu, okay? And 1 over 2 t squared. And finally, this n times small o 1 over n will give me small o1, okay? This is important. Small o1 is actually means that it's going down to 0. That's the definition of small o1. So that's why we can say this term is shrinking. It goes down to 0 as n goes to infinity. It's sigma squared, yep. is it no sigmas? It should be, let me see. I made a mistake here. This is not squared. So I should, yeah, that's a nice catch. Okay, so now up to this point, you can see the first two terms is canceling each other. They are equal. Okay, so therefore, now I let n go to infinity. Then this log, this is having a limit. This is 0. It's just 1 over 2t squared, right? So therefore, this is equivalent to say the MGF of Zn at t is convergent as n goes to infinity to exponential. I take exponential on both sides, e of exponential 1/2 t squared. So we're done, right? So with the MGF convergence, then by the continuity theorem, we have Zn convergent in distribution to standard normal. So that's the conclusion. That's what we prove for the central limit theorem. Okay. So it uses everything we have covered so far, including the MGF, including the continuity theorem, and also a lot of Taylor expansion in the middle. So we can approximate non-linear, non-polynomial function by a polynomial function. Okay, so that's it. So since we only have one lecture today, I think the homework I'm going to assign, so we still have weekly homeworks. So the homework I will assign today will be based on the central limit theorem. So you're going to apply it. And basically what you want to see is that when you do the approximation, you are going to assume this quantity follows approximately standard normal distribution. That's how you're going to apply it. And also you are going to do more exercise about the MGF, because I feel like that's something maybe most challenging for this class and the beginning, right? It's the most abstract concept you will face in this class, but it's a very useful tool for showing convergence in distribution, which is what we need for central limit theorem. Okay, so thank you all. And I'll see you on next Monday. Okay, thank you, bye. Bye.
Thank you, Professor. Professor,
Yeah, yes.
I have one more question. So what was the like small o mean was?
Small o is just a relation. It's a relation notation. So let me see. I lost it again. Sorry, I think I didn't know where I put it. So it's just a relation between two sequences. Again, I'm writing here again. When I say an is small o bn, it means an, both sequences are going down to 0. Okay, so an goes to 0, bn goes to 0. When I wrote this, small o means that in relation to bn, an goes down to 0 faster. So by faster, it means that the limit of this ratio an over bn is 0. So this ratio is 0. So that means it goes down to 0 faster. But so this is what it means. If I have the limit of an over bn equals to a constant, say 1, not equal to 0, in this case, I will say an and bn goes down to 0 at the same rate. They goes hand by hand. That's what we mean. But what we are using is here. We are saying it's faster. So therefore, that's why we said 1 over n squared is small o 1 over n, right? Because this goes down to 0 faster than this.
So which means so d is going faster. If I say o 1 over n means like 1 over n goes faster. So is that clear?
No. It's an goes down faster than bn does.
An goes faster than bn.
Yeah. Yeah, Bn is the basis. Bn is the reference, and An is faster than Bn.
But
So
if
that's
AN
why.
goes faster than BN, how can it be 0?
Think about this, right? Let me just give you numbers. So for this, 1 over n squared, when you change n, right? N goes from, say, 1, 2, 3, 4. This is 1, 1/4, 1/9, 1/16, right? And if it's 1 over n, it's 1, 1/2, 1/3, 1/4, which goes down to 0 faster. The former, the top line, right?
Yeah, that's true. Okay.
Yeah.
Okay. And then, Professor, I want to say, really
Yeah.
thank you for your patience. And so I'm trying my best, but sometimes I have to ask, even though you
Yeah.
told me before, I think I have to
Yeah.
ask. And then I do believe that is not only, it's not just my curiosity. I think
Right.
many students also like having struggle with me, but they don't express like me.
I
do
agree.
right
Yeah.
now.
So I
So
appreciate that. I think it's good to ask. I agree.
and
Yeah.
yeah, after that, like many people just say that it's hard, like I'm struggling. So I think it's pretty cool that you just having a patient to me and other students. I want to say thank you. And then
My pleasure. Yeah, I think it's okay that we don't go over all the plan materials, but I hope we can be clear about the things we cover, right? So it's better to be clear than faster. Yeah.
And then my last question is, I want to know, what do you expect students, including me, to do at the homework? For example, I'm trying to do my homework right now, and then it's quite really like don't know how to like even to start, you know. So I was you like suggest us like just try to Google, and if I Google it, and then there is some like website showing the answer, but before showing answer, at least I want to try make my logic and then set my steps to get reach the like answer. But even though I don't have like some basic like the knowledge about it, could you like any recommendation, give me like any recommendation to do it, at least like try to make a logic and then steps like.
I think it's about math proof. Honestly, I think it's about how to write a proof. And I think that's also something I think it's very difficult to make people on the same ground. It's also an issue with the prerequisite. So my suggestion is that if this is you want to really pursue this major, right? If this is something you want to major in, or you want to be at least pursuing a graduate school degree, I would say, then take a class that teaches you how to write a proof will be something very essential. And that's a long-term thing. And specific to this class, my suggestion is that if you can understand what I did in the class, you are on the good page. Yeah, because the homework problems are actually simpler than the lecture notes. And also the logics are very similar. And also we have this discussion section that goes over the homework solutions, right? So therefore, if you cannot follow a step, just ask. That would be the best immediate solution for this class for now. But long-term, I think taking a class that teaches you how to write a proof is necessary.
Yeah, I mean, yeah, I'm just trying. Actually, I don't really 100%, even like more than 50% understand right now. Actually, what I can do right now and what I'm doing right now, just let's take a look at the note and then write it down, same thing, and then just saying over and over again. And if I cannot understand, just watch your lecture again, and then just ask you like this in the class and then later on. But I think
this is, I would have to say, this everything here is math. This is math, right? This is not really statistics, it's math. But math is just an important tool for statistics, as important as computer. So that's why we have to teach you this. But later, right, you can decide what career choice you will go, you may not need to use math that much in the future. You may use programming most of the time, but this class is just the undergraduate core course. We hope to have everybody on the same page. So that's why for those of you who want to pursue advanced degrees of statistics, you have the foundation. That's why we have to teach this. But I think making up the math background is like a long-term job, right? Just like when you do exercising, you have to start from the basics, then you can do harder moves, the same idea. So that's why if this is something you want to make up, you have to pay efforts. Yeah.
Sure, I will do. And then
Yeah.
if you help me with like this, and then I think
Yeah.
I can make it.
Yeah.
And my goal is not just getting A. My goal is
Yeah.
getting knowledge, and so that I can explain what I learned,
Yeah.
the knowledge from this class to other people. That's my goal actually. I don't mind like just getting B or but more than B though, like anything anyway. Then my goal is that one. So
Yeah, I agree.
Yeah.
I think that's the purpose of learning, right? We want to understand things. So that's why I think the good thing about math is that everything can go to you can always go to the fundamentals and find a reason. It's just that some people, when you have different backgrounds, you may need to spend different amounts of efforts to understand the same thing. But the answer is always there. That's the good thing. There's always right or wrong.
Thank you, Professor. And then
Okay.
I'll talk to you later too. Thank you.
Okay,
Have
sure.
a good one, and then
You
have a
too.
great one.
You too. Bye.
Bye.
Bye. Bye.